So when we have functions that are functions of time, we do not use y prime. Y prime is off the table. So if I'm going to take the derivative of y with respect to t, I write dy over dt. If I take the derivative of x with respect to t, it's dx over dt. Remember, it's only when you take the derivative of with respect to x of x that you get 1, right? Okay, so you're being told that y is a function of t because they're saying find dx over dt if dy over dt is this. Okay, so let's take this and take the derivative with respect to t on both sides. So the derivative with respect to t equals the derivative with respect to t, and I'm just going to even write it as the power that it is. So derivative of y with respect to t gives me dy over dt. Here I take the derivative, so 1/2 x to the negative 1/2 times the derivative of the inside, which is dx over dt. Then remember, I've always said it's really, really useful to put those negative exponents in the denominator. Now when I do that, I'm going to plug in the dy over dt is 2, right? Put this into here. And then I'm going to plug in that when x is 5, so I put in the x here is 5, so that gives me 25. Sorry, put x is 25 in there, so you get 25. Then you just multiply it out, right? So then put this over here, so that'd be a 4, and then times root 25, which is 5. 4 times 5 is 20. All right, so let's do this one. So this is my equation. I'm going to be taking the derivative with respect to t on both sides. So this would be dy over dt. So this, to take the derivative of this, you know it can be useful to think of this as x to the negative 1. So it's negative x to the negative 2 times dx over dt. And again, rewriting it so that the negative exponent is gone can be really helpful when you're plugging things in. So let's go plug in dy over dt is negative 3. And we're plugging in x is 2. So I'd have a negative 1/4. And I'm going to find dx over dt. So then I get a positive 12 is dx over dt. Okay, so let's try another one. So this is saying this is my function, and I want to take the derivative with respect to t. So before I even take the derivative, I'm going to take the time to rewrite it as x to the negative 2. So I get dy over dt, negative 2x to the negative 3 dx over dt. Again, I'm going to rewrite it with the negative exponents in the denominator. And then I'm going to plug the information in. Okay, so I'm trying to find dy over dt this time, so I'm going to leave it there. I'm putting in x is negative 1, so negative 1 cubed, and then the dx over dt is 5. So negative 1 cubed is negative, and then negative negative is positive, so I get a positive 10. Okay, so let's look at this one. So here's my function. I'm given this rate. I want to find this rate, and this is the when information we use after the derivative. So to take the derivative of this, you get dx over dt, 3y squared dy over dt, and you know the derivative of negative y is just negative dy over dt. Then I just get to go plug the information in, right? Plug in y is 2. And I get to plug in the dy over dt is 5. Put that into both of those. And there's the answer. Okay, so let's try something like this. So I've given this rate, find this rate when information. So I'm going to go take the derivative. So 2y, y prime. I can't write y prime, can I? Oopsies. To write dy over dt equals 2x dx over dt plus dx over dt. Okay, so let's see what I can do. I can plug in x is equal to 2, right? So this is 2. I'm going to plug in. I'll carry the other 2 along. So this 2 carries. Do I know dx over dt? I think I do, right? Don't they tell me dx over dt is 3? So I get to plug that into two different places. And then I've got this green 2 that carries along. And then the dy over dt is what I'm trying to find, right? So that's okay to have there. Oh no! What about y? Oh, what about y? So I should, looks like I filled it in. So I don't know what y is equal to. So now let's go back and use our when information. So let's put x equal 2 into the original equation. So if I put x equal 2 in here, I get 4 plus 2. So I get y squared is 6. So I'm just going to say we're going to use the positive one because we're going to be talking about physical distances. So I'll put the root 6 here. And so then my dy over dt would equal, so here I'd have 4 times 3 is 12, plus a 3 is 15 over a 2 root 6. And that's the answer. Okay, let's look at this one. So here is my equation. If I take the derivative with respect to t on both sides, you see the product rule on the left-hand side, and you know the derivative of 4 is 0. So then if I plug the information in, if I plug in x equal 8 in here, and I put in the dx over dt is 10 here, I know I'm trying to find, right? So remind ourselves what we're trying to find. I'm trying to find dy over dt. So that's totally fine to have that in there. But how do I find out what y is equal to? So I'm going to go find out what y is equal to by taking this when information and putting it into the original equation, and that's how you can find it. So this is going to be a common thing. All right, so let's go try another one. So here is my equation. So I see the product rule happens on this side. So first d second plus second d first equals, and take the derivative of y is dy over dt, and the derivative of 6 is 0. Okay, so now let's go plug in. I'm plugging in x is 1, right? I'm trying to find dy over dt, so I'm just going to leave that in there. Plus, I don't know what y is right now, but I do know that dx over dt is 10. Equals, and I've got 4 times this dy over dt, which is what I'm trying to find. So let's go and use this when information into here. So I'd get y equals 4y minus 6. So negative 3y is negative 6. So it looks like y is equal to 2. So I can put y as 2 in there. So I'd get a dy over dt plus 2 times 10 is 20. Equals 4 times dy over dt. I'm solving for dy over dt, so let's subtract it. So I'm going to put an arrow, so I get 20 equals 3 dy over dt's. So 20 divided by 3 is dy over dt.